Should we start? Yep. Okay. Yep. And we're on, and it is Wednesday, I guess, February 24th. Chapter 21, the very end. We've covered all the reactions. We'll show you the protecting group issue right at the end of 21. We'll review a couple of reactions here to start. And then 22, which are the derivatives of carboxylic acids that we'll start today. Homework 6 is due tonight. Quiz 5 is posted. I've talked to a few people. In fact, I've been helping a couple people already with Quiz 5. So it is posted. Make sure you get a hold of that and get that uploaded by tomorrow night. Test 2 is next week. I think it's Wednesday through Friday, a little bit different timing. So yeah, we have plenty of time for chapter 22 and to help review for it. But the sample test too is already on Learning Suite. So if you want to start looking at that to prepare there. Okay, let's do a little review here on the side. And we've got 4 reactions, including a mechanism of one here. So the first one is what? A secondary amine, dimethylamine with a ketone. So what's going to be the product there? You have a 50-50 chance, an imine or an enamine. What's it going to be? If it's a secondary amine, the product will be what? Imine or enamine? I kind of heard everything. Let's see. Someone raise their hand and tell us clearly. What is it going to be? An imine or an enamine? I know they're very close, the two sounding names. What's the product here? Yeah. Enamine, okay, with an E. Okay, yeah. So it's going to be a double bond on the side between the 2 carbons, and the nitrogen will have the 2 methyl groups on it. Okay, and then here, this is pointing out the reverse reaction of the acetal formation. So here we have the acetal, and remember we said those are stable to neutral conditions in base. But look at this, they react under acidic conditions. So if you add strong acid with water now, you're going to go back to what? The ketone. And what happens to the methoxy groups? They end up as 2 equivalents of methanol. Now, that just gets solvated by the excess water, okay? But the acid provides a pathway back. If you didn't have the acid there, it'd be no reaction. That acetal and neutral water wouldn't do anything. But what's the mechanism? That's what we need to review, okay? But let's look at these 2 first, just the reactivity, okay? So here we have the Wittig reagent with an aldehyde. So what are we going to get here? What's our new functional group? Starts with an A, right? What is it? Yeah, alkene. Yeah, so whatever's on the Wittig reagent, 1, 2, 3, 4, right there. And then this carbon here is the carbon of the carbonyl. And remember, we said you don't need to worry about cis or trans there. Just get the connectivity straight. And by the way, that applies to quiz 5. I think there's a synthesis problem there. You get a trans epoxide product. You can make that from either the cis or the trans alkene, and I'd advise you to use a Wittig reaction before you do that MCPBA epoxidation. If you've looked at the quiz, you might know what I'm talking about, but if you haven't yet, that's a good hint there. So yeah, alkene. And then let's see, aldehyde or ketone, aldehyde in this case, with sodium cyanide and acid. That's going to give the cyanohydrin, which is going to look like this. Right. Okay, so all those reactions, make sure you understand the combinations of the starting materials and the reagents and what type of products you get. Now, a little bit on the mechanism here. These mechanisms are more complicated. We did the reverse of this last time. Remember we took the aldehyde or ketone, we reacted it with acid, and then we started adding alcohol to it, ethanol or methanol, right? And we went all the way to the hemiacetal, and then added another alcohol. So you can look at all these as just reverse arrows. But here in this direction, we're hydrolyzing, we say. We're breaking apart the acetal, or breaking those bonds with water. That term hydrolysis, maybe you've heard before, just means a reaction that breaks bonds using water. Okay, hydrolysis or lysis means to break, and hydro, of course, water. And here it is, protonate the acetal. This can become a leaving group now. And notice we're under acidic conditions, so we've got plus charged intermediates. Bring the electrons down, and then we have this intermediate, which is a cation there. And then what water can go on there? Yeah, we need to push the electrons to finish this, I guess. Then we have the protonated thing here. We can transfer the proton intramolecular or via the solvent, a couple steps. Don't worry about that. Proton transfers are fast, and so that can occur here. And now we have the protonated methyl ether over here, right? Then we can bring this lone pair down and kick this off. And remember, these have resonance structures. Anytime we have the double bond to oxygen with something else on it, we also have a carbocation here, right? And that's where, you know, the nucleophiles can add in that forward direction. But here, all we need to do to finish the thing now is what? Just deprotonate the protonated ketone. And this goes to the acetone. And that regenerates the catalyst, you can see. So the H plus just provides a pathway that allows us to go in either direction, depending on whether we have water present, hydrolyzing the thing, or in this direction, the reverse of the one drawn here, if we had excess methanol, okay, as a solvent. Do you see that? Practice those mechanisms backwards and forwards a couple times, and then it won't be so daunting for you. I know to have a 7 or 8 step mechanism can be very, you know, unnerving. Most of our mechanisms have been relatively simple to this point. I think this is where we start to get some more complex ones. But again, we got to transfer protons and get things on or off there that make that a little more complicated. All right, let's use this acetal thing to talk about protecting groups just briefly. This is kind of a minor topic, though. I don't want to belabor it. And here's the problem. Let's do it in the context of having a problem here. So here we have an alkyne ketone, 2 functional groups. And we want to use base here to deprotonate this guy and then add methyl iodide. We want to get to this, the methylated with a CH3 group here on the alkyne, okay? But if we use base here, and we can use a couple different bases, we could use butyllithium, that would be a good one, or we could use ethyl magnesium bromide. We could use the Grignard reagent, okay? That's certainly a strong enough base to deprotonate. Remember the pKa of a terminal alkyne? Let's see if someone remembers that. In 351, we went over it. What is it? It's about 25, yeah. So any of these conjugate acids you see, these are alkanes. That's 55. So that would be highly favored to take that off. We could use sodium amide. You know, any of these would easily take that off. But the problem is we've got a ketone present. So if we use the organometallics, they're just going to add here, okay? And they'll deprotonate here. If we just use one equivalent, actually we'll get a lot of addition as well. They're good nucleophiles too. So what do we do here? First, we treat with this material, which is called ethylene glycol. It's the common name, or ethane diol, 1,2-diol, and acid. So we have H2SO4 here. And what do we get? We get the cyclic acetal and the alkyne still there. Okay. And now what? Now we can treat with the ethyl Grignard. And you see now we don't have a ketone or aldehyde here. Now we're just using the Grignard as a base, right? So we can form the anion there. And we can put in our methyl iodide. And what reaction is that? That's our good old friend, what? SN2, right? Charged nucleophile, primary leaving group. That'd be very good. Now we've got our methylated alkyne. And how do we get to our desired ketone now? Oh, now we just take the reverse here. Water and sulfuric acid. And that will hydrolyze our acetal, okay? The acetal is an ether, okay? Ethers are inert to basic conditions, okay? Strong nucleophiles. We can't just add those and kick that open here. That would be an O- leaving group. That's not good. But a carbonyl like this would easily undergo nucleophilic addition. There's some other things here with strong bases. We can also take these protons off with the alpha positions. We'll learn about that later. But right now, this protecting group issue is an important thing. All right, one other quick topic on acetals here. And this is that sugar-related idea where you've got a alcohol in the presence of an aldehyde or a ketone, okay? So this molecule here only exists like this part of the time. Most of the time, it's going to exist like this, where it's going to add there, and it's going to form a new sigma bond, right? But I'll do the mechanism for you, showing you how you get here. And what are we going to call this? Well, it's an ether alcohol. And acetal is a diether. What did we call? We had another term for this. An ether right here on the same carbon that also has an alcohol. Remember what we called that? Yeah. Hemiacetal. Yeah. So it means halfway. And we saw that intermediate when we did the mechanism. Now, this is an intramolecular one where it's within the same molecule. So this actually turns out to be favored. In fact, at equilibrium here, 99% of the time, if it's a 5 or a 6-membered ring, this can be favored. And you can kind of see why. It's already in proximity, right? And a 5 or a 6-membered ring is strain-free. In fact, all the sugars we'll look at later on, the monosaccharides, and you saw glucose, I wrote that up on the board at some point, will exist as these hemiacetals. Okay, and it's because you get this extra sigma bond, okay, at the expense of a pi bond. Sigma bond's worth about 90 kcals per mole. A pi bond is about 60 kcals per mole. You still have the sigma bond here between that carbon and oxygen, but now you have the extra one, and it's strain-free, okay, and entropically, it's not requiring too much more order within the molecule, okay? So that's how it sits, as a hemiacetal. Now you can take this molecule and treat it with methanol and acid, okay? So it's already halfway to what? The acetal, right? And so this will be a mixed acetal. All the acetals we've seen before are just from methanol or ethanol or the ethylene glycol. They're symmetric. But here you can treat this hemiacetal, which is cyclized, treat it with more alcohol, and what you get is what? Well, you can protonate that alcohol out there. You can use your lone pair here to eliminate water, and you get this intermediate. Now that could be a carbocation here or a cation on the oxygen, okay? So that's an oxygen stabilized by the lone pair there. And then what, we're in methanol? So yeah, let's finish this thing off. And I'm not gonna do the next steps. You can do that. In fact, it's on the quiz for you to do there. So we're gonna get the full acetal now. And yeah, that's how this molecule will stay now. Under what? Neutral and basic conditions, this will be stable. If we go back, right, if we treat it with water and acid, look, we can go back to the hemiacetal. But it'll mainly sit as a hemiacetal. It's only 1% the open form. Okay. At equilibrium, it'll mainly favor. And why? It's because it's cyclic, it's intramolecular. 5 or 6-membered ring will be favored there for the hemiacetal. And that's the important thing for sugars. And we'll, of course, review that in that later chapter. But questions on this? And I think that's enough to help you with the quiz there, looking ahead. Questions on 21? All right, let's look at 22 here, carboxylic acid derivatives. And what we need to know, well, we've already talked about these actually. Acid chlorides, okay, and hydrides, we've used those a couple spots. We'll throw in thioesters and regular oxygen esters. You've seen those before. Nitriles, yeah, carboxylic acid, and amides. And what's the ordering here? This is reactivity. So the second level of understanding of OChem is reactivity. What combination of reagents give what products? You can form any product here to the right from any starting material that's on its left. Okay, and that's the key to this whole chapter. We can do a ton of reaction combinations now with different nucleophiles and different acid derivatives. And why are these called acid derivatives? Because the OH group is taken off. Well, there it is. There's the parent compound, the carboxylic acid. We can take that off and put on these other type of leaving groups. Okay, in nature, they're mainly phosphates, acyl phosphates that we see here. And why the reactivity here? Why is acid chloride the most reactive one, and amides are the least reactive? We'll have to look at the stability of that and the nature of that leaving group when it comes off. What does that conjugate base look like? If it's a weak conjugate base coming off, like chloride, Cl minus, which is happy as an anion, that's going to be what? A very reactive species. Okay. There's also a resonance effect here. The amides with the lone pair here on the less electronegative atom has a lot of resonance structure. And I've got a model here. We'll go through that. But there's a ton of examples, very diverse class of compounds. These are different than aldehydes and ketones now, okay? These have a potential leaving group on the carbonyl. So that's really kind of the key difference. But a lot of reactions, a lot of nucleophiles, including some that we know here. And then we'll look at them separately. The most reactive ones are the acid chlorides. We can react those with a lot of nucleophiles, including very mild ones, and make anything to the right. So you can make anything from an acid chloride, okay? The other key thing is we can convert the carboxylic acid to the acid chloride with thionyl chloride right here. So we can make any of them. And because these are all derivatives of carboxylic acids under strong acidic aqueous conditions or basic conditions in water, we can convert any of them, including amides, to the carboxylic acid. So there's a lot of flexibility here. And in biology, we'll point out these couple here. We'll do an anhydrides, anything to the right of the anhydrides. We'll do acids. We'll make esters from the acids, the Fischer esterification. We'll hydrolyze esters. Esters are the most diverse ones. Why? Because they're of moderate reactivity. And in metabolism in cells, you want something that's stable enough, but reactive enough also. So we'll see acyl triglycerides, and we'll see phosphatidylcholine diesters in membranes. These are all esters, okay? And there's a reason why esters are important. They're of moderate reactivity and stability. They're not like amides. Amides are rocks. They're not easily hydrolyzed. And that's the main bond in proteins, by the way. That's what holds us together. Acid chlorides are just too darn reactive. In the lab, they're very good. But in biology, they're actually toxic to cells. But there's a lot of things to say about esters. That's why we'll spend quite a bit of time on them. Amides, very stable, but we can hydrolyze those back to acids, you see. We'll talk about some drugs and penicillin, thioesters. We'll throw in nitriles also. Here's the issue of stability. And I like this graphic. It brings back your old friend NMR, which is kind of cool. So here is a solvent. It's called dimethylformamide. 2 methyl groups here, and then this hydrogen here on the side of the carbonyl. It comes from formic acid, right? Common solvent. Well, if you take the NMR of this, you actually see 3 signals. These 2 methyls are actually different at room temperature. Why is that? Because that's a single bond. You should say, oh, if that's freely rotating, those 2 methyls would be the same, right? But no, it's not freely rotating at room temperature. There's a barrier to this rotation. Why? There's a lone pair not shown here, right? That can come in and come down here between the carbon and nitrogen and then push up the electrons onto oxygen, right? To what degree is that resonance structure part of the actual structure? A great degree. There's a tremendous amount of resonance stability here. So these 2 methyls are distinct at room temperature. If you heat up the NMR sample here, you can do that in the instrument, these 2 peaks eventually coalesce. which is kind of cool. In fact, you can measure this barrier of rotation using this NMR experiment. It turns out to be about 20 kcals per mole to rotate around that carbon-nitrogen single bond, to break that carbonyl nitrogen lone pair resonance, okay? And we'll look at the models and go through that a little bit. In a practical sense, these carboxylic acid derivatives are all over the place. You can examine drugs and see esters, carboxylic acids, amides, more esters, another amide down here, sulfonamide here, which is kind of related. Another amide, yeah, ester. Cocaine has 2 esters there. Methamphetamine, no. I think that's the only one without anything. FK506, the immunosuppressant, there's an amide right there. Oh, Prozac doesn't have one either. Okay, so no derivatives there. Or morphine. Yeah, so, they are very common, but, they're not in every molecule. But you should be able to identify those and know what we're talking about. Membranes, I just mentioned that. A lot of esters, acyl triglycerides in adipose tissue. And that's because metabolism, those need to come on and off, depending on the needs of the organism. So you need a derivative of moderate reactivity and stability, not one that's a rock. Now, how does this work? So here's the array. Here's the most reactive one. Here's the least reactive, the amide. Why? We're going to have tetrahedral intermediates. All the mechanisms are the same, which is the nice thing about this chapter. It's the hierarchy of reactivity, though. Keep this in mind. It's due to how good this is as a leaving group, right? The weak base coming off here comes from a strong acid, right? pKa of HCl -7. That means that's the weakest base. That's your best leaving group. It also has minimal resonance here, okay? So it makes the attack on the carbonyl very fast, and then the leaving group coming off. Whereas the amide, looking at this guy, all this resonance stability, and then if you bring off N- with 2 pairs of electrons, that's the worst one. That's the strongest base, okay? And that's the weakest acid, the protonated form of that, the neutral form. So we'll keep that in mind. Look at that. We'll look at some cofactors too when we get to the thioesters. And I think that's it. Oh, that's more fatty acids, yeah. We'll say more about that later, but let's go to the board and do some of these. The ones we need to look at here, and the general mechanism. I'd like to get the general mechanism on the board here. That's kind of the key thing here for the reactivity. So let's see. Reactivity, they're all derivatives of carboxylic acid, so it has the carbonyl, and then, the different groups on there, and all of them have the same mechanism. You're going to be bored by the mechanisms, if you aren't bored already by the mechanisms. No. Use the mechanisms to help you out here. So what we have for the derivatives is some X group there. It's not hydrogen. It's not an alkyl group. So it's not an aldehyde or ketone now. You got to keep that distinction in place. We've done a couple chapters in a row where we focused entirely on aldehydes, ketones. Now we're on derivatives of carboxylic acids, where X is a heteroatom, okay? Oxygen, nitrogen, or halide here. And what's our reaction? Well, we have some nucleophile here, push the electrons up, O- X, and nucleophile. Okay. Now what can occur here? Tetrahedral intermediate, right? We go from sp2 to sp3 hybridized, just temporarily. O-, it is higher in energy here. And then what? This comes back down. And we get that on there. And you've got a feel for this already. Chloride's going to be very good, so that'll be a very fast reaction. If we have N whatever 2 minus, that's going to be very slow. Okay, so that kind of tells you there. A key reaction to help you out here is all these derivatives, okay? Any of these with water and acid or hydroxide, okay? And sometimes we have to heat these up, especially with amides, okay? They don't go very fast, even with forcing conditions, strong acid, strong base, and water. And we go to the carboxylic acid. Okay? So all of the derivatives can undergo this reaction. Some very fast, acid chlorides, anhydrides. Some super slow, amides. Okay? Get to this, and then the key reaction you can always do is this. SOCl2. That's called thionyl chloride. We've seen that before also, right? That can be used to make the most reactive one, okay? And from that one, we can make all the others, okay? And just depending on what nucleophile we put in there, right? So I like to show this. This is the flexibility part of the chapter, the versatility, you can say, really. Synthetically, we can make any of them. We can hydrolyze any of them, okay? So from any source, we can make the key one, which is, they're all derivatives of this guy. And then thionyl chloride, and then make the products. All right, let's do a little bit of naming, hopefully not much. They are, esters are a little tricky to name. We'll keep this simple and straightforward. We will show you how to name them in a simple way, and we'll just look at a few examples. Okay, so acid chlorides or alkanoyl, OYL chloride. Okay. So the simplest one shown here would be ethanoyl chloride. And I'm not going to keep drawing chloride there. Or we could call that acetic or acetyl chloride. And so, how do we get this alkanoic acid? There was our parent. Take the ic off and add YL. And same thing here for the common name, acetic or benzoyl chloride. So I think that's enough there. This OEL chloride thing is kind of the key there to name it. There are acid bromides, acid fluorides, acid iodides. They're just not practical. The bromides are more reactive. The chlorides or the fluorides are less reactive. They're harder to make. And the iodides just aren't stable. So we almost always go with the acid chlorides, okay, alkanoyl chlorides. All right, anhydrides. We've seen these before. These are alkanoic anhydride. And where does the term come from, anhydride? We've lost the elements of water from 2 acid chlorides. And we've seen this one before. This is acetic anhydride. We could also call this ethanoic anhydride. I'm not going to draw it anhydride a bunch of time, but that's the name of the acid it came from, right? Ethanoic acid or acetic acid anhydride. You can also have mixed anhydrides. You can have this one. So there's 2 carboxylic acids that came together here. What, propanoic acid? And what's this acid over here? That's methanoic acid, or there's that common term, it starts with an F, right? Formic acid. And you just alphabetize these 2. So this would be methanoic. Yeah, there's a lot to write out here. Propanoic, and then anhydride. Yeah, and those are kind of rare and hard to use, but they're hard to make, actually. You make them from the acid chloride of one and react with the acid of the other. It's not too bad, but the names are kind of bad there. Normally, they're always symmetric, like acetic anhydride or formic anhydride, stuff like that. Okay. Let's get to the harder one, which would be esters. Okay. And esters, like we said, they're of moderate reactivity, and they're literally a breath of fresh air. Carboxylic acids are some of the nastiest smelling things you can get, especially butanoic acid or pentanoic acid. Those guys are really nasty. Everything from body odor to bad cheese. Okay, yeah. But if you make the ester, then these things are very pleasant and very nice smelling. And the key here is you've got 2 different R groups. You've got an alkyl group over here on the carbonyl side. Then you've got an alkyl group on the alkoxy side. And that's kind of how we talk about esters. They're named as alkyl alkanoates. Oh, 8. Well, that 8 term comes from taking the ick off, okay, of alkanoic acid. They are derivatives, right? This alkyl, technically there's a space here, so there's a YL prefix name. Actually, the alkyl here refers to the alkoxy, the R prime part, okay? And then the alkanoate, as you can imagine, that's the parent. That's the R group, okay? So that's why I said they're a little more complicated. But they're kind of fun. Let's look at a couple of them here. How about this one? Some of you have probably used this in different labs or classes. This is what? Ethyl referring to this group here. And what's this over here? Ethanoate or what? Acetate, okay, is the common way to name that. The 8 here taking the place of the IC. So ethyl acetate. Anybody use that as a solvent anywhere? Yeah, it's a common solvent, ethyl acetate. How about this one? How about that one there? Now this is a little more complicated, but the alkyl group here in the front is still the same, ethyl, okay, and that's YL space. And then what's our parent? 1, 2, 3, 4, 5. So it's pentanoate. Notice I'm using a big space there. Why do I need a big space? Because we've got an extra group on our parent. So this is the 1 position, 2, 3, 4. So what do we have? We have 4 methyl. Okay, and then this part here, no space, that refers to any other substituents we might have on the parent. So there's a space right here, ethyl, 4-methyl, pentanoate. So I kind of jumped ahead to a little bit harder problem there. But I think you can see this 4 refers to where on the pentane is that extra group found, okay? And then the prefix here on the alkoxy part is what you list first, okay? So ethyl pentanoate. Now, this will help us keep track of some of these structures. Let's look at this one versus this ester. And so, yeah, you can use these to help you keep track of structures. What are the names of those two? Let's see. We've got ethyl here in the front, all right? And then what's our parent? Our parent is what this acid came from. What acid did that come from? Starts with a B. Benzoic acid. So what are we going to call this? Ethyl what? Take the ick off. And what? Benzoate. Very good. Ethyl benzoate. And, take the IC off. Add the 8. Ethyl benzoate. Is that the same as this ester here? These are the same molecular formula, same ratio of atoms. But look, the ester's in a different spot here, right? And this is not benzoate now. This is acetate, okay? And what's on the alkoxy part? This whole thing here has a prefix name. It also starts with a B. Anybody remember what that is? A benzene with a methylene. It's not a phenyl group. It's actually what? A benzyl group. Yeah. So this is benzyl as a prefix name, okay? That's the alkoxy part. And then what's the parent part, where the carbonyl is? That's acetate, okay? Oh, so there's a jumble of words for you, right? Ethyl benzoate versus benzyl acetate. Okay? And that's what I think is good about esters. We know how to make those separately, and if we hydrolyze those, we give different products. So the name can help us actually keep track of the structure and the reactivity, okay? So anyway, that's a good one to keep track of. All right, let's look at amides and nitriles real quick. Amides are actually, for some reason, well, no, nitriles are more difficult to name. Well, I'll just stick with a simple name for those. And same for amides. So let's see here. So here's a simple amide. Here's the general name, alcan. Take the E off now and add amide. Okay, so that's reasonably simple, but it's a little different variation of how you get the base name. So what is this? This is ethanamide, okay, from ethane, or what do we call that? Acid amide, okay. Acid amide from the common name, and there you take the IC off at the end. Benzamide, similar way. But they're a little bit different, right? This is from the common name. This is the systematic IUPAC name from the alkanamide naming there. Well, so let's do a couple of these and hopefully not too many more. So here's a methyl group on the nitrogen on the benzamide. So we name it as a propanamide to get the base parent name, but that's only this part, right? How do we handle that methyl? Well, it's going to be a prefix name, but here's the difference. If we just use a number and methyl in the front here, that's really referring to the parent. How do we differentiate this position for substituents versus having a couple groups on the amide? Well, we put it out here, N-methyl, okay? And there is a space there, just like esters. So N-methyl propanamide, okay? That's different than calling something like this. That would be what? That would be 2-methyl, not designating this capital N out here, okay? 2-methyl propanamide would mean what? We'd have at the 2 position an extra methyl. So that makes naming a little trickier, I think, for the amides, but I think you can see that. And we'll stick with the simple ones, okay? There are 2 positions. We could have this guy if we had N then, and then we need a di right here. N-dimethyl propanamide would look like that. And yeah, you do need to say NN to make it clear that you're referring what? To the nitrogen here of the amide, okay? It looks like you got 2 nitrogens somewhere, right? No, it's the position marker. This is the N position where these groups are, okay? To differentiate between this, which would be on the parent. Okay, let's look at nitriles. And nitriles, what do we got here? So we got triple bond there. Remember, it is a triple bond, so it is a derivative of carboxylic acid, alkane, and then just nitrile. You don't take off anything there. Or we can call these cyano, or alkyl, sorry, alkyl cyanides. Okay, and let's stick with these 2 ways to do it. There is another common name, alkanonitrile. If you use this name here, make sure you count the carbon of the nitrile. So this would be propane nitrile. But if you use this approach, alkyl cyanide, now it's whatever alkyl group on the cyanide you have. So that's kind of a substituent kind of naming too. So this is ethyl cyanide. Okay. So 2 different ways to name those. Sorry about that. Yeah, there actually is a third. I'm not going to do that one, but I think this one's simple enough, confusing enough, you could say. So new, different ways to name things there that can be a little bit tricky. There are a couple other names here of cyclic ones to keep track of. And these are cyclic esters now, intramolecular esters, okay? We call these guys lactones. And that's an unfortunate term, I think. They don't relate to lactic acid, and they're not ketones. It sounds like they're ketones. But these cyclic esters here are called lactones. This one's alpha beta gamma lactone. This one's alpha beta gamma delta lactone. And that's referring to the Greek letter position there of how far down the chain is the oxygen coming back to the carbonyl. Okay. So yeah, we got those. We also have lactams, TAM there. Lac is also in there. And let me show you a couple of those. They're cyclic amides. Okay. So if you have alpha, beta, gamma, lactam, it's a cyclic amide. And then the famous one, the drug family, is this one. These are what? Alpha, beta lactams. The beta-lactam family of antibiotics, what's the prominent member there? Starts with a P. Some people are allergic to it. Penicillin. Okay, there's hundreds of penicillin variations in the pharmacopoeia that are used currently in the clinic, and they're all beta-lactams. Okay, so we'll see those later on. Just the generic names here, lactone, lactam, need to be aware of. Okay, we'll see them later when we get into it a little bit. All right, let's get into stability, structure, and let's start with the most reactive one, acid chlorides. And I'm going to do a little comparison here of all the structures and talk about the relative reactivity of these. So the most reactive one are the acid chlorides, which means a nucleophile here can be very fast, okay? And why is that? There's a couple things here, right? This bond is polarized that way, which makes that carbonyl even more electropositive. And this is a long bond. It's about 1.8 angstroms. That's super long. A carbon-carbon single bond is 1.54 angstroms. And plus these lone pairs here. What? It's a very electronegative atom, 3.8 on the Pauling scale. So it's holding on to these electrons very tightly. They're not available to resonate, okay? So let's say no res here. All these factors, electronegativity, make this nucleophilic addition very fast, okay? And then that's the leaving group, right? Which is part of the electronegativity issue, okay? So they kind of go together there. Let's compare it to this, though. Let's have this anhydride, okay? Well, we have this same bond here, okay, which is electronegative toward the oxygen. So nucleophiles can still go here, okay? So this is still very good, okay? Reasonably fast reaction. And I do have the kinetic data here. The K here for this rate constant for hydrolysis, I think of acetyl chloride, is 10 to the 11th. Huge number. Remember that rate constant is in the rate equation? The rate equals K times the starting material in the nucleophile, which is water in this case. And that rate constant relating those two is actually 10 to the 11th power. It's almost diffusion controlled. It's done in seconds. You put that in there. This one is done in minutes. It's still very fast. But look, you got resonance here, and the oxygen is less electronegative. So, but look, it's between two atoms here. So you're resonating on both ways. And so the way you're not resonating toward is still available for that to attack. And then you still have a pretty good leaving group, right? You have acetate coming off as a leaving group. So these are still very good. What about this? So an ester, ethyl acetate, whatever. Well, you still have the electronegativity here. But look, you have this resonance happening over here, which helps out this nucleophilic attack of the anhydride. Whereas here, all the resonance is localized here, and there is some resonance there, okay? So they're still okay for the reactivity with a nucleophile, but they're going to be slower, okay? It'll take hours to hydrolyze that with water, okay? And that's what you want for metabolism. You want something that's stable enough, but, you know, is going to eventually react, okay? Let's see, what's the other one? Oh, let's just jump ahead to amides, okay? And compare with this now. And I'm kind of drawing these sideways for a reason, because I want to point out the lone pairs here on amides. Why are amides the slowest? These are the worst. Okay. Nucleophile attack here. Very, very slow. Okay. Why? Well, it's just the opposite of all these other factors we just pointed out. This is now what, 2.8 on the Pauling scale? So this pair of electrons is held out further. In fact, it rehybridizes into what? A p orbital. So the nitrogen is sp2 hybridized. The lone pair is in a p orbital. We'll look at the model here in a second. What's that going to do? That's going to make this available to resonate. So a lot of resonance, okay? And look at that, O minus and double bond character there. What's that do to that bond length? Do I have the bond length? I hope I do. Yeah, look at that, 1.34 angstroms. A typical carbon-carbon double bond is what? 1.31 angstrom. This is almost there. And a true carbon-nitrogen single bond that doesn't have any resonance involved, that's 1.47 angstrom. It's a little bit shorter than a carbon-carbon single bond, which is what, 1.54 angstrom. Now, don't memorize these numbers or anything, but know the trend here. A lot of resonance, a short bond here. So you see the nucleophile can't get in there because this is donating electron density in there. It's just the opposite of the chloride. Let's look at the model here, and we'll relate that to that experiment, the variable temperature NMR experiment. Let's see, is that showing up okay there? Here's our carbonyl, our pi bond of our carbonyl. The oxygen's red there. Here's our nitrogen. Hopefully you can see that it's blue. So that is an amide. And I'm differentiating the two hydrogens or the two alkyl groups on the nitrogen there. And look, I'm showing it as sp2 hybridized. Why? Because that lone pair is now part of resonance here. Actually, these, electrons, there's 4 electrons in this allylic pi bond system, right? There's 3 p atomic orbitals. Well, if that's resonating there, look, if we try to rotate, this one is right now cis, you see, to the carbonyl, so with the blue bond there. If we try to switch it over to trans, what do we have to do there? We had to temporarily break the resonance, right? And that's about 20 kcals per mole barrier. It's not a true sigma bond, single bond. It has a lot of double bond character, up to 20 kcals per mole. And again, why did nature select the amide to be the key bond between amino acids and proteins? Because it's super stable, very slow. This holds us together. Without this bond, Pauling calls it the peptide bond, okay? This peptide bond or amide bond, because of this extensive resonance stabilization, lower electronegativity accentuates that, makes this attack of nucleophiles a lot slower. This can take years. In fact, let's see the rate constant here. And don't memorize these. This K here can be 10 to the minus 5, which means we're on a geological time scale for hydrolysis. Yes, we can hydrolyze them with strong acid, strong base, but on their own, under neutral conditions and mild conditions, they're going to stay there. Whereas these guys are going to fly apart almost instantly with neutral water, okay? Questions here on the stability here? We're talking about a few different things, right? Electronegativity, the size of this atom, even though there's 3 lone pairs here on the chloride, no resonance, okay? Why? Because it's a longer bond and high electronegativity. A lot of resonance here because lower electronegativity rehybridizes and has extensive resonance donation. And then kind of a mix here between anhydrides and esters. Questions on that? Okay, let's get into the reactivity. We got a minute or so. Let's do the key reaction here. And I call this the key reaction because it opens up all the others. And all the other reactions are just variations of the tetrahedral intermediate, right? So any acid chloride. And again, we can get that from any of the derivatives, right? With water and acid and sometimes heat, including amides. We can hydrolyze amides. So any of the derivatives will eventually go back to the parent, the carboxylic acid. And then from here, thionyl chloride. And maybe let's draw out thionyl chloride. Um, I've never put the mechanism for how this reaction works on there, but let me show you why it works maybe. You generate a molecule of sulfur dioxide, and you generate a molecule of HCl. And sometimes you have to heat these up if the acid's kind of hindered there. But what do you see here? An oxygen coming off here, combining with the sulfur. One chloride will have to be a nucleophile. There'll be a tetrahedral intermediate, actually. You can figure out the mechanism. But what I like to point out is these are both gases. HCl is also a gas, unless it's in water. There's no water here, though, right? We want the acid chloride. So these will both come out of this solution and what? Drive the reaction. Why? Because entropy is increasing greatly, right? We're forming these two gas molecules, which is part of the reason why this works. Thionyl chloride, SOCl2, going to the acid chloride. And from there, we can make all the various derivatives, okay? So, it's kind of a redundant pathway here, but it shows you how you could convert one, say an ester or an amide, back to the acid, carboxylic acid, and then convert it to an anhydride, for example, or a different amide, okay, depending on what nucleophile you. So it points out the flexibility, I think, and we'll defer on the mechanism there. I think you're okay with that. All right, let's start one here. Let's start with the carboxylic acids, chlorides, and do our first reaction. So we will go through them sequentially. Friday, Monday, you'll see we'll do all of them. So here's your simplest one. What's the mechanism? Put this guy in water. Okay. What's going to occur? Well, push the electrons up. O minus, OH2. Okay. Now what? Well, a couple things we could do. Could transfer a proton over here. We don't need to do that, actually. You can see we can collapse either tetrahedral intermediate. Let's just collapse this one. What do we get here then? We get the carbonyl back. We got OH protonated form of the carboxylic acid, and we've got chloride. Okay. Well, this turns out to be a super strong acid. The pK of that is like -9, -8. That's the protonated form of acetic acid, right? So what do we do here? Well, we go to the carboxylic acid and HCl. Okay. Yeah. So there's your first one. Our next one will be ethanol with pyridine. We'll have some pyridine in there. And let me give you one more. We're going to have, we'll do the one with acetic acid also. And we'll have some pyridine in there. And the pyridine will be useful to soak up the HCl because our products here will be an ester and an anhydride. And if we have too much HCl or water building up in here, we can go back there. And that acid can affect our product there. But yeah, and then we'll do amides from here, right? So we'll have some sort of a amine there, and we'll form amides, okay? But the mechanisms are all the same there. So very good. Questions real quick on anything? We've done a lot, nomenclature and reactivity. All the reactions will be variations of that. Keep in mind the hierarchy. The most reactive one, acid chloride, least reactive amide. And you can make any one from any other one as long as you're going to the right there. Okay, that's the key there. All right, very good. Thank you. We'll see you next time. All right.